Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, well, thank you for coming back for part 3. Appreciate your stamina. So the points that are on the docket for today all concern this overall computational scheme, gradient symbolic computation. And I'll just review a few points, 0 and 1, before we get into new material. The first new topic will be optimization, how to understand grammar as optimization, and how to understand knowledge of language as knowing what properties expressions should have, as opposed to knowing a procedure for manipulating symbols. So that's a new theory of grammar I'll tell you about, or a pair of them actually. And then, time permitting, we'll get into how discrete and gradient combinatorial representations can be useful for linguistics. We may not get too far into that today. I don't know. We'll have to see how it goes. Okay, so as far as reviewing is concerned, the first point here, understanding neural networks requires an abstract computational theory of cognitive function. And so on the first day I argued that linguistic theory has an important role to play in giving us the kind of understanding at an abstract level of what is required for competence in language. So the second review point here, I'll take a little bit of more time on. Cognition is computation over combinatorial structures. And this gives a new theory of neural encoding. So this is the tensor product representation idea that I've been talking about for quite a while. And I mentioned something about it to Lee the other day, and he thought it might be of general interest, so I will pass it on. And that is relating tensor product representations to tensor product atoms. So this is our formula for tensor product representations for, let's say, a tree. The vector that encodes the whole tree is the sum of vectors, each one of which encodes one of the constituents of the tree. And each of those is the tensor product of a vector for the role within the whole structure that the constituent plays, or the position in the whole structure that it occupies, times the content, the filler material, the content of this constituent. So that formula is actually ripped off from physics, I have to admit. These are atoms. And actually, they are particular orbitals for electrons in the periphery of an atom. And the formula for the state, which is a vector, it's a vector in an infinite dimensional space, and it's a complex as opposed to real valued vector, actually. And there is such a vector for each position in space here, and its interpretation is telling you about the probability of finding an electron at a given location x. It's proportional to the square of this vector value there. And the state vector for the atom looks like this. The vector for the atom is the sum of a bunch of vectors, each one corresponding to a particular electron. And for each electron, there is a product of the vector that describes its role in the atom, which is the orbital it is occupying. And that's multiplied with the tensor product times the vector that tells you the internal state of the electron, which is reduced to only a spin value, one of two spin values, actually. So that's very simple in this case.
Yes, so the correspondence, this is in Schrödinger equation one in quantum mechanics.
That is the vector that the Schrödinger equation.
Role filler in this tree corresponds to.
So the roles are the orbitals, and the fillers are the internal states of the electrons.
The number of internal states is much smaller.
But much smaller.
It's plus 1 minus 1, 1 0
Yeah.
or something, and
Yeah.
this one is a lot. It could be 50,000.
The tree.
Yes.
The
Yes.
tree is
Okay.
Yes. So what we're doing is much harder than atomic physics.
And the row in your tree case, binary row is 1 0 0 1. Just have two row vectors. Whereas in physics, how many choices do you have for the octals?
Lots.
So it's bigger role in
Well,
physics
there-
than in cognition.
Well, there are two roles for binary trees that are primitive roles, but then you recursively use them to generate infinitely many embedded roles.
Is that
So,
comparable in size to physics orbital, the choices of octal?
well, for atoms that have a lot of protons in the nucleus, then they have a lot of electrons around them, and a lot of orbitals are filled. But the atomic numbers, they don't go up past, what is it, 250 or something? I don't know.
Smaller than the cognition.
Yeah. So nothing compared to sentences. Okay.
So in this case, the operation on vectors that's basically the element-wise product. And this
What product?
Element-wise?
Does this correspond to the element-wise product on vectors? This tensor operation? You said you generalize it to higher dimensional space, but in this case, vector you mean like one-dimensional vector, right?
Well, I mean the vector in the infinite dimensional space of particles, which includes areas. The bottom part?
Yeah, not in the physics part, like in.
Oh, okay. I'm sorry.
Yeah.
The product here
Yeah.
is the outer product of these two vectors. So it's the product of each of pairs, one element from this vector times one element from this vector. So it's the outer product. And there is some confusion over notation, I guess. I didn't use this. This is, as far as I'm concerned, the standard representation of tensor products. But I understand that engineers use it for something else. And so it could lead to some confusions. But it's just intended to be the outer product, if that.
Okay, so the point is that if the tree is recursively growing, then you do that repeatedly.
Yes.
Therefore, you get higher dimensional array.
That's right.
Not just two-dimensional. The way you are writing down is like two-dimensional.
Right.
Algebra.
Yes, except that this thing here could be a high-dimensional array itself. Okay, and I've mentioned my interest in trying to reverse engineer networks that are in the business of producing natural language, looking at the states of the hidden layers to see if we can interpret them. And so I wanted to tell you about an approach that we've developed for doing this, and which has been tested only on synthetic data, not on anything real. And that might be useful to try it on some real networks. So here's what this algorithm does. So given a set of vectors, each vector is the state of a hidden layer in a network, let's say. And each one corresponds to the network processing a different input, or potentially a different time in the processing of an input if it's temporally extended. The problem is to interpret these vectors to understand how they represent the domain data, and to do so in order to enable us to explain how they can successfully compute the outputs that they compute. And the hypothesis behind this method is that the vectors are tensor product representations. And so what you have to fit in to the data are the parameters of a tensor product representation, which are, first of all, for each input, what are the fillers and roles that are instantiated in that input? And second, what are the vectors that encode the fillers and the roles? So that problem can be stated in terms of a generative model. So we assume that there's a process for producing those tensor product representations that we've been given, and we're trying to infer backwards to the source of these in terms of filler role combinations and vectors encoding them. So I'm going to switch to matrix notation. This is work largely of a colleague. It was all programmed in MATLAB, so everything is written in matrix notation as opposed to tensor notation. I told you I'd warn you if I was going to be switching, and I'm switching. So this is the tensor product representation written in matrix form. So we sum over all of the roles in the structure, the outer product of the vector that tells us what symbol or structure fills that role, times the vector R that encodes that role.
So that case, R is the vector, therefore transpose, vector by vector, you get auto product. But what if R is also high dimensional in terms of
Well, then
tree
you should
structure?
then you have
the
to flatten
transpose-
it out into a long
The lower, okay. And then
vector
the
in order
transpose.
to be able to use matrix notation to do it,
Okay.
which is one of the inconveniences of matrix notation for this purpose. So, all right, so in order to identify the constituents that are in a particular tensor product representation, what we have to say is for each role, what is the filler, or possibly null filler? And that can be expressed through a binary matrix, that is to say a matrix whose elements are all zeros or ones. And so in row F, column R, the matrix has a 1 if that role has that F as its filler. Otherwise, it has a 0 there. So, for example, here in this binding matrix, B, it tells us that there are 3 rows here, 1 per column, that the first role is filled with the 4th possible filler. The 4th symbol is located in the first row. The 3rd symbol is located in the 2nd row, and the 1st symbol is located in the final 3rd row.
Is there exactly one non-zero thing per column?
Yes,
Okay.
yes, that's right. So we add a null symbol in case there are roles that are not filled by a real symbol. We use that one as the place to put the 1.
Could there be 2 ones in the same row? Or is it
Yes.
all- Okay.
Yes, so the same symbol could appear in more than one position. Okay, and so if we take the product of the matrix that, each of the columns in this matrix is the vector encoding of a role. There are 3 roles, and each of these is a vector encoding of a filler. There are 4 possible fillers. And if we take this product, what we get is exactly this. We get the sum of the outer products of the filler indicated by where the 1 is here for the role indicated by the column. And
But the filler in the original F sub R is a vector. Now in this new notation, it becomes a matrix.
F sub R is one of the fillers, and so it will be either this column
I see,
or this
okay.
column or this column. And for the first role, according to this
Okay.
matrix, it's the 4th column that we actually want to use. We want to take the outer product of this vector here, which is the 4th role,
Okay.
a 4th symbol, and we want to use that to fill the first role. So we want to take the first column of this matrix and take its outer product with the 4th column of this to form the tensor product that encodes the first symbol. And then we add to that the product of, in this case, the 3rd column of the filler matrix times the 2nd column of the row, and we add that to the first one.
Yeah, so in that case, that binding information is lost in the original representation. So why is binding information like B, whether the structure of the B, reflected in the original summation notation?
That's the whole point of unbinding.
So,
You can find out which filler is in a given role by unbinding that role. You take the T, and you take the inner product with the role vector that you're probing with, and what comes out is the filler vector for that role.
I see. Okay. So just by looking at the equation, you don't see where it is.
Right.
Okay. Whereas in the matrix notation, you can see that right away, just by
Right.
looking at the structure
Yes.
of the B.
Well, this is this refers to a single particular structure.
I see.
It refers to 4, 3, 1.
Okay.
But this is general equation that refers to
Okay.
any structure.
Okay.
So although they are mathematically equivalent, the representation power of both
It's identical.
is not different. Because B is not represented in the first equation.
It's implicitly represented by which fillers are
Oh, I see.
bound to
You
which
have to
roles.
write, a lot of.
It's not explicit, but it's
You
implicit.
have to write a lot of superscript, subscript, denote that. Probably. Okay,
You would
you do
need
that.
to do something like that. And so to the extent that the B matrix is limited in the way that we just discussed, so that there's only a single 1 in each column, then the number of degrees of freedom is the same.
So now, if the R here, row, is higher dimension,
Yes.
which you said you are going to put them together in the R vector, then you don't have even dimensionality matching here in terms of metric multiplication. How do you resolve that? Discrepancy?
No, you would.
No, if my R, suppose, has
I mean,
higher
right
dimension.
here, R has, the vectors
There's
R
one
here
dimension
have,
for each.
length 3. There's nothing particular about length 3. It just happens to be chosen for this example. So that could be a really long thing, which is a result of flattening something, and it wouldn't change the formalism.
Can be modified to fit that.
Yes.
Okay.
Well,
So it looks like here they're not linearly independent. Is that the columns?
they ought to be. They ought to be.
They don't have to be orthogonal now.
If Don didn't give us linearly independent vectors, I'm going to have to fire him retroactively because he quit quite a while ago.
They don't have to be they don't have to be orthogonal because
They don't have to be orthogonal. That's right.
Okay.
They aren't. Okay, so all right, so we're doing a generative model. This is just a formula that describes what it is we're generating in terms of something more basic. To generate a binding matrix which determines what particular combinations of fillers and roles we have in a given instance, we note that each of these columns in the matrix B is a indicator vector with one single one. We assume the roles are marginally independent, and we let beta FR be the marginal probability that a particular filler F fills the role R. And then we just have a multinomial distribution for the probability of a given B matrix. It's just beta for each filler role combination raised to the power either 1 or 0, depending on whether that binding is present. Then we assume that there's Gaussian noise in this space where this matrix lies. So we assume isotropic noise, some variance, and what we're calculating here is the mean of that distribution. So the full joint distribution then is the probability of x given b times the probability of b. And we have those equations to combine.
Yes, so the x dimensionality of x is how much in this example? It's the same as the 3 by 4.
So x is a particular point in the space where these t's lies, right? So in terms of graphical model depiction of the situation, we have the tensor that's generated, x, results from a choice of binding for each role, and each of these guys is a variable that tells you which filler has been chosen for that role. The outer product is with the F and the B and the R transpose. So these are also used to generate x. And then the distribution of x is also governed by the variance of the noise. So the choice, the normal, lazy choice is to use conjugate priors on the parameters here. So we have hyperparameters that are the parameters of the prior distributions for the probabilities that a given filler fills a role, the filler vectors that are just randomly generated, some mean and variance, similarly for the roles. And then we have the usual distribution for the inverse variance. Okay, now there are various ways of trying to then do inference with this model, given a set of vectors, which are the values of this observed values of x. X is a matrix.
Where does the matrix come from? I mean, where does the data come from? As matrices.
So we're trying to reverse engineer a network. And so the network gets a lot of inputs, and for each input, we observe the state of one of the hidden layers, and that's one of the vectors. And that's right. So we have to analyze the vector as a matrix in order, as part of this process of.
There are many ways to unwrap the vector. matrix.
Yeah,
Yes.
I have
That's right.
exactly the same question here. So suppose, I mean, this general model only can give you probability measure. So if I give you, maybe a weight matrix from my DNA for speech recognition, or Jacob give you whatever for translation, then you apply that model, and then you learn parameters, and then for the different set of, data, you can actually compute the probability. So what probability for generating X, which is the weights on DNA, for example, for X, the matrix. Is it? Oh, is it activity?
Activity.
Is it activity? Okay.
So the question is, if the activity is a vector and we're trying to generate a matrix, how do we get those to connect?
I suppose it's multiple instances. But
And
is that?
no,
No?
I mean, you have a sample of these x's, but yeah. So what I should say is that I guess I omitted an important transformation here. So in the synthetic data that was used to test this, the algorithm, we chose F, R, and B vectors. We generated them randomly. We knew what they were. We produced these matrices X, and they were in the form of matrices. And so the data was given in the form of matrix for the synthetic data. In order to connect this to real data, I propose that there's another matrix transformation from this space here to the vectors that we actually observe that has to also be estimated. So that, yeah.
And what is the sense as to how sensitive that estimation is? Because you can adjust your F and R to deal with all kinds of transformations and so on. So I'm guessing you don't have to be really precise on that matrix. So can you just wrap it just trivial ways? Just say I'm going to reshape this into a 3x5 matrix or whatever it is, and then hope that the algorithm is going to find a good fit, or do you still have to find a good way to reshape?
I don't know whether it's too much too strong a constraint to require that the number of elements in the vector be the product of a length of filler vectors and the length of roll vectors. That might be too constraining, especially if it happens to be a prime number or something. And so,
the usual thing where you just expand it a little bit and so on. But I'm wondering, just the geometry of reshaping, does it mess with the estimate, or because you have the freedom to choose F and R, you will somehow adapt?
There's an arbitrary choice in the sequence of ordering of the of the vectors in each of these F and R matrices, and so that gives you a lot of room for changing how the linearization would go if you arbitrarily picked one. So I don't have experience with it, but I think you're right about that point. Okay, and so the only thing I have more to say about this now is, so Don Mathis, who developed this algorithm and the code, tested it on synthetic data, as I mentioned, using 3 different procedures. One is an analytic version of expectation maximization that involves explicitly summing over all the possible B matrices, which obviously is a big restriction. So if the set of roles and fillers, the number of possibilities of the matrices for combining them is limited, then this is a possibility, and he got about 50% success. You might hope for better success with such a strong limitation.
You have to set the threshold to say that if the probability going beyond that, you said there's a match. Otherwise, you can match anything. What is it? That's what I thought. I give you.
So this is synthetic data. I know what the filler and roll vector matrices are supposed to look like.
Oh, I see.
So you generate all the B's and F's and R's, and then you use it to produce X.
Yep.
So then you pretend like you didn't know what they were and try to optimize them back.
Precisely.
And do you say that it's a success if you can match the original? If you can match the original, wait. How do you define?
Yeah,
what
exactly.
is
The same question.
It's a question of matching up to various symmetries in the system. So the reordering of the columns in the F and R matrices, obviously you can't eliminate that degree of freedom. And so
you could explain the data equally well with something with a different matrix. How is that not? It's not a local optima. That's just a different. I mean, it is technical local optima, but I mean, it's equal. It's impossible to, if you have two things that can explain the data equally well, you don't get, and you arbitrarily chose a different one. Then how can you say that that's not a success, or define that?
I wouldn't say it is not
Okay.
a success.
So
I would say it's a success.
So do you do it based on error rate, or based on, or like, you know, reconstruction error rate, or based on the actual values of the?
The actual values of the estimated Fs and Rs and Bs, and sigma for that matter, were compared to ask, is there a rearranging of the columns relative to what was generated, and such that then the matrices that are estimated line up, with the exception of one more degree of freedom, which is undetermined, which is if you multiply the F matrix by C and you divide the R matrix by C, you'll get the same result when their outer product is formed. So up to some multiplicative constant, is there a match? And
Is it, so these are hugely over-parameterized, right? So you should always be able to, like, be able to reconstruct X is not an issue, right? You can always get something that can reconstruct X perfectly. It's just that because there's a number of free parameters. Like, what is the order of magnitude of the number of free parameters relative to the size of X, to the number of values in X?
I don't know what sample size he used for X, so I can't answer that. But we're talking about how many different instances of X are in the sample, right?
Well, but generally, if you can perfectly reconstruct it, right? If you can perfectly reconstruct all the X's in your training data, you know, up to some epsilon, then why wouldn't that be the criteria for success?
Oh, I don't know that it's any different in reality.
I think the experiment only tests whether your optimization program is powerful enough to estimate your original parameter. So
Yep,
you
that's the
can
point
use
of
the
this kind of
parameters
test, right?
you know to generate data, and then you pretend you don't know the parameter. You use the algorithm to learn.
Mhm.
If you know get the estimation to be roughly right, you declare it a success. And that's the way to test the program.
Yeah.
You can always do that well, but not for the real data. Then you don't know what generates the data.
That's the point of
Then
using
how
it,
do you
right?
know whether it's successful or not? Whether there is a TPR?
Well, then you would use the probability of the data that you're estimating from.
My original question is that what kind of threshold you have to say that beyond the threshold it's good, otherwise it's bad.
That's not how evaluation is done. I mean,
No?
you know, we can compare models.
So like, if you were to apply this for real data, how would this be now? Okay, so if we give you a bunch of vectors for a recurrent neural net or something like that,
Right.
and then you can factor them, and you can factor them in a way that's you get very low reconstruction error. How is the result any more interpretable than the original?
Okay, so then the next step is to say, okay, now for each instance, each input, we now know what the roles are, what the fillers are of each role. So then we can ask, what does being in role 1 mean? If we look at all of the examples that have a particular filler in role 1, what do they have in common?
Okay, so the actual values of the FNR matrices are not so interesting. It's more interesting.
No, they're not interesting at all, as a matter of
What
fact.
the B's are. Okay.
Yeah, that's right. It's really the B that's going to carry information.
What we look like, that's what they present.
Yeah, I mean, at least certainly the R and F matrices are a much lower order of importance. If we were using neural data, they would be more interesting probably than they are for artificial neural nets, but it's really the B's that are going to tell us how to interpret it.
So intuitively speaking, the B is just a structure, right? In the underlying structure of the tree. So
Yeah.
the experiment is to see whether given X we can recover the structure.
Right,
Right.
right. Or we can recover the structure in a set of instances of X.
So in that sense, the accuracy metric is based on the structure, right? It should be based on B.
Right. Yeah. I mean, I think that enough instances were used that it does not appear that there was any problem of underdetermination of the variables aside from these symmetries that I already mentioned. I don't recall that there were issues of finding lots of different solutions on each run or something like that.
The strain binary matrix, so you can't really rotate. You can rearrange things, but you can't produce new solutions by rotation of the basis vectors.
Right. So there's not, eliminating that degree of freedom means that the integrity of the columns and so on is more intact.
So, if you were to analyze real data, you have this underlying assumption that the activation vector is constructed via a TPR mechanism. But I would propose that there's more than one way to represent the type of knowledge, not just TPR. So is there something that, like this whole reconstruction would only work if the actual real network somehow used TPR? So do we know that that's the case for some reason? Or
We do not. We do not. It hasn't been applied to trying to reverse engineer any representations that were not already constructed to be tensor product representations. So I do not know. But let me try to rephrase what we're trying to accomplish in this analysis. It's just a rephrasing of what we're interested in is B. So we're asking the question, is the set of states of this hidden layer a combinatorial set? Is each one a different combination of some fixed stock of elements with their roles switched and which is combined with which switched? That's what we're asking. Can we see the vector set in those terms?
How many there's the size of the two vectors and then the number of fillers and the number of roles, so there's four important hyperparameters?
So for each role filler pair, there is a prior probability that filler will fill that role. So that's the biggest set of unknowns. And then this assumption of this particular work was that there was a common, well, I guess, sorry.
Your particular optimization, but how many hyperparameters were when you generated the synthetic data? There's four, right? There's the size of the two vectors, and then the size of the number, or the four or three, right? Because it's either the size of the two vectors and the number of roles, or the two vectors. And then
so to generate a sample, we do exactly all of this. We have to pick an F, okay? So there's a lot of choices there. We have to pick an R, a lot of choices there. Right?
You generated the same mechanism, the same way?
Mm-hmm.
Oh, okay.
Yeah.
So the only parameter you estimate is better.
No, we estimate them all, but in terms of generating synthetic data, we have to produce a particular set of values for all of these variables here. And this is a matrix, so it has a bunch of different choices. And of course, there are a bunch of these, so there are lots of choices to make.
I mean, you're just using this representation for it because it's mathematically optimizable, but you don't necessarily think that it actually falls under this distribution for real.
Right.
I mean, you don't have any reason to actually believe that, like, for real language or whatever, that beta would fall under a Dirichlet distribution or anything, right?
Yes. I mean, I don't know that there's a single case of this that will work, let alone know that over the whole population of ones that work, the distribution of betas is a Dirichlet distribution. So pretty far from being able to have any empirical input on that question.
So let's look at the empirical results to see what kind of reason you have.
Well, they're very sparsely described here. So I mentioned the first one. In the second one, instead of trying to analytically solve the EM equations, use Monte Carlo instead. Success rate was not great, but only one sample was used per iteration, and so there are lots of ways to try to explore doing Monte Carlo more effectively. Gibbs sampling was a method that was relatively doable at with a large number of bees tested, a large sample of different binding matrix possibilities sampled. And the success rate there was 30%. And so there do seem to be problems with local optima. I don't think there are problems of multiple solutions yet, but there are certainly problems of local optima. Anyway, that's the little bit that I have to say, aside from the fact that there's MATLAB code for all of this. And as I said, there is a crucial bit of the generative process which I think we will need to add, which is a matrix from the X here to whatever size vector space our hidden layer has.
So I don't know what agree with me. The real way of testing whether that neural activities have contain the TPR structure would be simply to replace that part of the neural network by this generative model and use that to see whether discrimination will be higher.
Yes.
With a real test. Otherwise, you don't know how high you should gonna match.
I'm not sure that this is what you're saying, but some months ago I pitched to you two projects. This was the reverse engineering project. Then there was the engineering project, which is to take this generative process and stick it into as a kind of generic replacement for hidden layers in a DNN where these parameters are what get learned and the representations are.
To be learned by backpropagation.
Yes, they have to be learned by backpropagation, but the representations themselves are constructed to be tensor product representations. There's no question about whether they are. There's just a question of what roles and fillers should be used in this problem and how should they be best represented.
So in that case, if you believe that it's true, you don't even have to do all this one. Because this one you suffer from local optimum backpropagation system getting through that anyway. If the result doesn't show good,
it's true that there's a sense in which the prior probability for this reverse engineering working may be lower than the prior probability for the forward engineering project to work.
Suffering from the optimal problem, you may not be able to estimate B right anyway.
Yeah.
So that's kind of more technical problem.
Right. Okay, so maybe I should go on then to the new stuff for this lecture. Computation in grammar is optimization. So knowledge of grammar is considered not to be a procedure for rewriting symbols, but rather a set of properties that a well-formed structure ought to have, constraints, and the theories of grammar that result from that, what I want to tell you about here. And it all starts with this observation that in certain neural networks, the computation builds an activation pattern that maximizes something that I call harmony, but we're actually interested in harmony viewed at two different levels: the level of the network, microharmony, and the level of the symbols that are encoded in the network, which I will call macroharmony when I need to be explicit about the difference. So microharmony is the extent to which a state of the network conforms to a set of micro desiderata that are encoded in the connection weights. And so here's exactly what that means in a super simple example. Suppose we just have these 3 units in our network. Here's one connection, which has strength -2, inhibitory connection. So this is a micro desideratum that says A and B should not both be active at the same time. And specifically, what it says is if they are active at the same time, then we should assess a penalty of 2. We should subtract 2 from the well-formedness measure for the whole state, and that is the harmony of the state. So we subtract 2 from the harmony, as opposed to a connection that's excitatory, strength +3 is the example here, and that represents the desideratum that they should both be active simultaneously, and if they are, we get a reward of harmony of a magnitude 3. And the harmony of a state of the network, which is an activation pattern, given a set of connections, which encodes all the desiderata, the harmony of a state of the network, the activation pattern, is just gotten by summing all of these contributions together. That's the crucial weight-dependent part of the harmony anyway. So that's all very easy to understand. Now, if we assume that the activation pattern in the network is a tensor product representation of some symbol structure, then the number we get from this process can be interpreted as the harmony of that symbol structure. And then we can think about grammars as telling us what constitutes a high harmony symbol structure, what constitutes a well-formed symbol structure. So harmony is a well-formedness measure. Originally, it's a well-formedness measure defined for network states, but using the tensor product representations, we can then take the value we get up to the harmony of a symbol structure. And those macro desiderata that describe the well-formedness of combining symbols together define what we call a harmonic grammar. So let me give you an example.
Yes, so there's no rules to this grammar.
There are just constraints.
That's right.
Yep. And
But there's still symbols, right?
so at the macro level, there are symbols. The micro level, there are activation patterns. You can talk about harmony in both.
Thing is called macro and micro.
Yeah.
Only
Yes, I would say so, yes. Yes, I think that's the best. Here is an example of one of these macro desiderata for syntax, and that is a sentence has a subject. Another one is that a sentence has no meaningless words. These are two constraints that were proposed and studied extensively very early on in this work as it was applied to syntax. So let's ask, how do we express a proposition reigns? Okay, so present tense, reigning is happening. That's what we're trying to express. Now, there's a conflict between these two constraints in this case. It's impossible to satisfy both of them because there isn't any actual subject for this predicate reigns. It has no arguments at all. So to put a subject into the expression for this would be necessarily to put a meaningless word in. So those two come into conflict. And the same thing occurs here. If both A and C are active, then B is getting contradictory requirements imposed on it. One to be not active because A is, and the other to be active because C is. And it's just the simple a summation of all of those forces that determine whether B should be active or not.
Connection to the symbols, like rank the words over here with the state.
Tensor product representation is the answer.
I see.
So you just have to imagine that this is a big network, that the activation pattern is a tensor product representation for a tree, and the tree has the word reigns in it, and it may have a word for a subject as well.
Okay. So I would say that it reigns. You put meaningless word, I.
Yes, that's what we do in English.
Okay. And the hope is that once you put it in there, the harmony is going to drop not as much as if you leave out it.
The harmony will be higher if you include it than if you exclude it, for the weights that correspond to the grammar of English. Because in English, it's optimal to incorporate the word it in the sentence it reigns.
Yeah. So this is not true to say that A may correspond to reign, B may correspond to it.
No.
No, it's separate.
No.
That would be local. Right?
That would be a local representation, and to some extent, we use local representations behind the scenes to create networks that will do the right thing for syntactic purposes. But better to think about reigns as a distributed activation pattern that's determined by the outer product of the vector for the word reigns and the role that it plays in the sentence
So A
in which it appears.
The value of binary 0 or 1, or does it take the value of the whole vector?
Which
A,
little a here?
B, yeah.
These are just single numbers, single real numbers is the idea. That's just an ordinary unit in a network.
Oh, I see. Okay.
That's what it's intended to be. In order to express reigns, we have to take into consideration the relative strength of the competing forces or desiderata. So the stronger force here wins, and it's the one that says B should be active. So that's what's optimal in the network. And then at the macro level, when we're talking about symbol structures, what we can do is we can think about There's a tensor product representation for rains. That's the sentence that has no subject. There's another tensor product representation for it rains. Finally, there's a representation for it rains it. And we can ask which of these has the highest harmony, because what we started with is that computation in certain networks will build an activation pattern that has maximal harmony. So what can we say about the pattern that should be built? If the network incorporates the constraints as they are manifest in English. So let's assume that we can assign, for the purpose of this example, a strength of -3 to the subject constraint. And so this is a constraint tableau that we're looking at here. This is the first column of it. There's one column for each constraint. The star here means that this expression violates that constraint because it has no subject. Whereas these two have a subject, it, so they don't violate the constraint. And if we compare all of the options here with respect to this one constraint, then we see that this guy is going to lose. And the exclamation mark tells you that that's a fatal violation. It is no longer in the running for possibly optimal expression. These two, though, are still in the running. And then what I guess I should have said was that, I just committed a major error. So what I was just describing to you was the way these tableaux work in optimality theory, which I haven't introduced yet. And that's a version of this theory in which this constraint has absolute veto power over this constraint. But actually what we're working on now is harmonic grammar, and so what I should have said was that the violation here causes this expression's harmony to decrease by 3. So as far as the harmony calculation goes, where we are after assessing this first constraint is -3 for this guy and 0 and 0. Okay. Now we go to the next constraint here, full interpretation. It's weaker in English, so we'll give it not -2 as its cost. And here we have a violation of that constraint because the word it does not contribute to the interpretation of the sentence. And this option violates it twice in virtue of 2 its. So the harmony associated with each of these 3 options is -3 for this violation, -2 for this, -4 for the 2 violations here. And so we can see that the best option is, in fact, it rains. It satisfies the stronger of the 2 constraints that are conflicting.
So what does it require TPR representation?
Doesn't.
In this example?
It doesn't.
No, it doesn't. Right?
No, this is the macro. We're talking at the macro level. Okay, and so this whole thing was constructed by asking the question, if we have TPR representations at this level and we have a network that's maximizing harmony, then what should we expect the output of the network to look like? And that's how this formalism arose.
So macro level tells you why it should be -3, -2 rather than -10, -100.
Sorry.
So
No,
the role of micro level of TPR representation.
It doesn't tell you that.
No?
That's where you implement those numbers, but it doesn't tell you what the numbers are. You need to do some sort of learning to figure that out.
Sorry, the -3, -2, like.
Where do they come from?
Yeah.
I'll just show you what happens in Italian, and then we'll see what's relevant about them.
So can we understand harmony as a sort of, it's like, sounds to me it's like a language model probability.
It's like a score.
It's like a score.
It's like a score.
So itself the score is produced by some underlying model.
You learn.
And the model is learned through neural network, right?
The model is implemented in a network, and the learning can be done either at the symbolic level or at the neural level. Learning what the weights on the scores of the...
And the 2 sort of parameters need to be learned from
Right,
the data.
that's right. So you can think of these as features in a Maxent model, and these as the weights of the features. It's very much the same story, but earlier, a long time ago. Yes?
So you'd have different macro desiderata for like different moods in English or something like that? Or like if it was a command form where you drop the subject, then you have another macro desiderata that would be separate from this one.
So The idea is that if we've done it right, these should always be at work. So in a command, there might be a constraint that overrules the subject constraint in virtue of being stronger than it. So rather than saying that this constraint doesn't apply to imperative sentences, we say it always applies, but then there's something else which is special that applies to imperative sentences that says something like, you know, if the verb has the imperative feature, it should have no subject. And in order to get the result we want in English, that would have to be stronger than the subject constraint to overrule it. So that's the way the game is played.
Right. How many macro desiderata are there?
Exactly, for English.
How many?
Macro desiderata might there be?
How many rules are there in your grammar book?
Grammar book.
Well, it depends on the OT analysis, how many of these you'll have. But they're doing the work of you know, traditional grammarian rules to some extent, and so that's the number you would expect of them.
So have you worked out the full set of English for syntax, for example?
No.
I think that would be debatable no matter what, right?
I don't think anyone has undertaken to do a very wide coverage grammar of English using these kinds of constraints, not to my knowledge.
For phonology, you have worked out the whole thing.
No, we just worked out lots of parts of phonology. So we could add together the constraints that have been proposed for all the parts of phonology that have been looked at, and the number would be in the hundreds, I'm sure. You might want to use a computer or something. Hi.
So to back up at a high level, what we're trying to do is gain some interpretation of a neural network for probably some very hard tasks where we can't actually understand what the network has learned, right? Am I with you so far on that?
Well, I should have said that I'm actually kind of changing gears in the new material here in looking at how to construct networks that do things we want, as opposed to reverse engineer networks. I apologize for having omitted that very important comment. Now, I have given some thought to whether, just like with tensor product representations, that was originally an engineering problem. How can we build representations that have these properties? And then you could say, well, having learned that, could we use that to somehow reverse engineer systems? And I've given some thought to whether the same thing could apply here, but it's less clear to me.
So with these constraints, I'm trying to construct a model that behaves well on my task. Now, if I don't have a complete set of constraints, which I think for very hard problems, it's guaranteed you will not. I can't enumerate all the grammar rules and all the discourse rules and things like this. How much does it hurt me if I'm missing those constraints? Does this mean my model won't be able to learn those phenomena, or I might just abuse other nodes in the network to explain the same thing?
Well, I think that there are certain distinctions that you'll end up not being able to make. So, like we were just talking about, you know, commands. So there's a distinction between whether you should or shouldn't have a subject, depending on whether it's a command or a declarative. Okay, you'll get that wrong. You'll get one or the other wrong. You won't get the distinction if you don't have a constraint like the one we mentioned that is sensitive to the difference between some imperative feature on the verb or not.
Couldn't the network learn this in a different way? Or is that exactly what these constraints do? They prevent the network from learning?
So we are almost all the work that's been done on learning grammars has been done, well, the vast majority has been done under the assumption that we know what the constraints are already. Some work has been done in the context of having a hypothesis space of possible symbolic rules that refer to different features in phonology. What rules should we form in order to best explain the words of English? But I don't believe that any work has been done to try to work at the neural level to figure out what these constraints are. So I think for the purposes of this part of the material, it's good to think about the neural level as implementing the stuff that we're really trying to work out at the symbolic level. And the neural level tells us things like the way to do grammar is to assign penalties for violations to constraints, as opposed to with sequences of symbol manipulating operations. So its contribution is at the level of the framework as opposed to the level of the particulars of a given grammar.
So in this hypothetical task, you're saying, given it, you get a sentence and you want to predict whether or not it's a grammatical sense or not?
It's really more like you have a meaning you want to communicate, and you're trying to ask which expression in my language best expresses that. It's not so well adapted for the grammaticality task, actually. So you've been waiting a long time. Thanks for being patient.
Something that could be done, or I'm thinking there should be something that could be done in between these two slides, where you are actually looking at realistic data, or you're generating data using your model over there, and you're then trying to fit that data to a simple, maybe two-layer network, and then trying to make connections. One possibility would be to just look at, I don't know, digits, for example, and then train an RBM, and then look at both the hidden variables and the observed variables as one set and try to wrap them so that you can explain it with a bilinear model, or show mathematically that they do fit it, and so on. But I'm saying something in between, generating and fitting the model, and looking at more realistic constraints and trying to infer them. But looking at smaller sets of data, simpler data than this. You could even create your own simple grammar and generate things based on that simple grammar and try to express it in both ways and see what the
I think that would be worth doing, absolutely. Yep.
So I would have asked less clearly what John also asked. So I am really interested in, can we look at the networks and discern what must be the macro desiderata? Because having written a grammar myself,
right,
there's an infinite number of these desiderata that are going to pop out. No, the more I look at language, there's always something going to pop out. I mean, like the subject and the full interpretation, you get to 80% so quickly, and I can do that in less than 100 grammar rules, for sure. But to actually explain the full scope of the English for any language, it's going to be, now you're talking, constraints upon constraints upon constraints in order to kind of craft it so that it does exactly what you want. So we kind of stopped that line of inquiry, and because we have a grammar that works, it works well enough, but you never get to really understand why does it work. So for example, with the command, and this ties back to AMR, right? So with the commands, we might want to, you might analyze that, go there doesn't have a subject, not at surface level, but at the subsurface level, at the meaning level it does, and that's what AMR does. It brings in these hidden, misunderstood, right? And so for example, with the macro desiderata, with sentences having a subject, I was sitting here thinking, don't agree. And that would have been a perfectly valid thing, say, don't agree. You would have known that it was I that's not agreeing. So it's the understood. We have a lot of understood arguments that are not there at surface level. But I think you might see them at kind of, if you represented, I think at a neural level, you might see that, hey, I know that there's going to be some subject there. I just got to go look for it, what makes sense in the context. But there's got to be some.
Well,
so you're saying there's no way macro desiderata to
I'm
keep
not,
everything in
I'm
the
not
macro.
saying it's.
I
personally am
emerge.
interested. Can we look at the neural models that are being learned, and as if we had a microscope, do we see evidence for there to be a subject or not? It's we linguists think that there are such things as subject. Maybe they're not. Maybe it's a mix of two different roles. Maybe Panini had it wrong all along. I don't know.
I wouldn't have such a heretical proposal, but I totally agree that that's what I'm here for.
What task do, because like a language model, it's saying predict the next word given the words that I want, that I've seen so far. That's not what we're trying, that's not what this is trying to be applied to. So
right.
What would a task be that we could actually train a model for, like, right, that you could then either reverse engineer or try to forward engineer that would be good for this?
Well, the process of taking a logical form and turning it into a syntactic expression. That's the direct mapping to the way the theory is set up. So you want it to produce it rains in English. You don't want it to produce it rains it. So you can't say that using words like it is free in English. If it were free, you could just put one here too, but you can't. The harmony is lower if you put it there. So English penalizes the use of meaningless words, even though we use them.
Is going in reverse a worse task or equal task to taking a service form and trying to produce a logical form? Is that?
It's worse.
Okay.
So let me continue. So in Italian, the story is that you don't say it rains in Italian. So in Italian, you get the right result by reversing the strengths of the two constraints. So full interpretation is stronger. Now you see that it rains is violating the stronger constraint now, whereas just rains is violating the weaker constraint. So its harmony -2 is the best. You still don't want to say it rains it. Nobody ever will want to say that. That can't be optimal no matter how you rank these, you weight these constraints. And so the idea is that what you want is, a task that you want is to start off with some potentially relatively language neutral meaning representation, and then be able to generate the optimal English expressions for a given meaning, the optimal Italian ones, and so on.
So the purpose of micro level is to provide the information about the penalty. Is it the purpose of doing that, or is it just
well, it implements the penalty, that's for sure.
Okay. But you have method of running the neural network to come up with the best.
No. I mean,
But you label enough data, maybe you can do that.
Possibly.
So that the constraint is minimized minimum in terms of label data. Because otherwise, if you randomly choose by you may not be able to get the minimum maximum satisfaction for the control you set up.
Right. I mean, there are. I think I mentioned that there are programs. There's linear programming programs that take a set of constraints and a set of candidate expressions and produce solutions for the weighting of the constraints that will give you the result that you want.
So in that case, there's no need to have neural network.
Right.
Yeah. So in that case,
yeah, nobody uses neural networks for any
to
of
do
this.
that, I see.
The thing is that you people who do DNNs use neural networks to generate language. We don't. And so the question is, what's the connection?
I see.
Yes.
When you take in Italian from machine translation and you could say rains in English, you just don't because you don't see it often enough, right? You always put out it rains.
Right.
But it's not doing it for the reason that, hey, I need something like a subject. It's not doing it for that
because
reason.
training data has like this.
Kind of
It's just copy
that
training
reason,
data.
So I mean, this is kind of classification from translation, because you could think of, if you're doing a sequence model where you read in the full source, generate a hidden vector, and then produce the target, that final source vector is really a logical form of the
Has subjects.
it's really a logical form of the input. You know what I mean? So yes, like you have a Chinese sentence, and then now you have some intermediate representation of Chinese. We don't know to what extent this is just like we don't know exactly what this vector is representing, because it could be like an intermediate logical form. It could be just a very simple set of. It could just be like a pretty little encoding of the Chinese, or it could almost actually be the English, right? Because we don't know how much. Because we have these two networks. one that encodes and one that decodes. We don't know how much work each one of these two networks is doing. So the interesting thing would be if it's actually kind of mapping it to a logical form, and then the decoder network is kind of decoding that logical form.
Right.
So it's like you have some sort of embedded representation, and the closest word you can find to that doesn't really have a lot of meaning, so it's it. Because that's the thing that's kind of like the catch-all.
Well, because the English decoder would hate the bigram startup sentence reigns, or it might hate like the trigram startup sentence reigns absence because it never sees anything like that in English. So it would know that in this scenario where, you know, you see like in Chinese where you see just a verb, that you have to produce something before the verb, depending on the other stuff that you see in the sentence.
Or in this case, not depending on the other stuff you see in the sentence.
But that doesn't correspond to any sort of subject representation.
Although in
That's
a
like the
neural
opposite.
model, you could
So the
imagine.
point is that the micro level, neural level really is just a way in the theory to implement whatever you have. But
Yes.
for practical purpose, throw away neural level, just do this according to the theory.
Well, for the practical purposes of the linguist, yes. But of the computational linguist, it's an open question whether throwing away the network is the thing to do.
Wait, so but if you, for machine translation, if you have a language where you know you can put the words almost in lots of different orderings, and then in English you have like the subject always comes first, then it would have to learn a subject representation, right? In order to, it would have to like kind of analyze the whole source sentence, parse out what the subject is, and then know that that's the first thing it should do.
So stepping back to the previous part of the talk, if we had a whole bunch of input sequences, and for each one we knew what that the hidden vector was that would be then sent to the decoding module, then we could ask what are the roles in that. Is it possible to see those as different combinations of assignments of fillers to roles or not? And if so, what are the roles? Is there something that corresponds to a role like agent, or is there something that corresponds to a role like subject, which is different? We would look to see whether the component of the total sum that gives you the vector that you're looking at, which is contributed by a particular role, is it the same for two sentences that have the same agent but different subjects? Or is it the same for two sentences that have the same subject but different agents? That sort of thing.
Yeah, I think that would be possible. But so one thing, so your model is completely linear, but you're not trying to claim that you can do all this stuff with a linear model, basically. It's that generating the B vector that's the part that is still, like if you were to actually train, like let's say train your model with the BFR representation with backpropagation, the hard part would be generating the B, because the B vectors are like F and R are free parameters, so those are just fixed matrices, but B is some transformation between your raw input, which is just the text, to generate this B vector. And so in that case, you would still have to have this complicated set of this complicated set of nonlinearities and recurrent networks and stuff like that, right?
I guess so. I mean, the interpretive question is ignoring, I mean, it's just looking at one small part of the picture. So it's not asking how does the decoding work such that, I mean, ultimately, once you understand something about what information is in this hidden vector, maybe you can then use that knowledge to understand the decoding as saying, okay, this is the part of the decoder that inserts something at the beginning because there's the knowledge that a subject needs to be there.
So you have these three matrices, right? The BFR. But the role matrix B, getting from the surface form to B, is still the hard part, right? If you're actually like not in the reverse engineering, but in the true model, the hard part is taking your surface form of the sentence and generating the role matrix, right?
The B matrix.
Yeah.
The binding matrix.
Yeah.
You would always know.
I guess so. If you already know what the other two matrices are, that's the only thing left to do.
Right. So, but that's basically like, so, but that doesn't really solve the problem of how do you you know, like if we had, you know, like that basically assumes that neural parsing is, you know.
We're not asking how that got there. We're just asking what is there. You're asking how does it get there. I'm not asking how do you know what the B matrix should be for a given input. I'm just saying, what is the B matrix for a given input?
But that's just in the reverse engineering one, right? In the true one where you actually want to, because you said there were two projects, the other one where you actually want to learn it. In that one, how to actually generate the B is the hard question, right?
Yes, we haven't gotten to that at all. I mean, by at all meaning not even close to getting to that part of the picture. It doesn't use, it uses recurrent networks. Let's see here. Okay. Okay. So the point from the theoretical point of view is that by positing that these constraints are present in every grammar, we can make the prediction that there'll be some languages that work like English and produce it rains. There'll be other languages that work like Italian and produce rains. There'll be no languages that produce it rains it. Obviously, if we had more than just two of these constraints, there'll be many more possible patterns of outputs that could result by differentially weighting them. And so this is a theory of typology, which is the study of how languages differ from one another in what types of languages are there with respect to the use of subjects, for example. So there's a typology of subjects, and this is part of it. And the theory we're talking about now makes predictions about what the typology should be once you posit certain constraints as the content of what's usually called universal grammar. So that's the main innovation of this line of grammatical work. There wasn't really a theory like that ever before. Okay, so this is just two constraints, very, very simple situation, but still actually the subject of actual papers. But a more complex case that is closer to something you might feel is realistic is below. I don't know in what lecture we may get to it, but it's about phonology as opposed to about syntax. Okay, so let's see here. Now, what the next several slides do is explain, show you why it is that there's that there is a harmony function that's maximized by a class of recurrent networks. Actually, we're now interested in networks that are recirculating and which have connections that are symmetric. You might have noticed that in this picture here, the connections are all symmetric. So this inhibits that one with strength 2, and this inhibits that one with strength 2. But they're bidirectional.
So the number, the 103, is related to the strength.
It's related to this, yeah. But if we had a local representation of everything, then it might actually even be the strength. But in a distributed case, that number 3 in the macro grammar would be spread out over lots of connections. But that is exactly the locus of the information about strength of constraints. Okay, so I think I should probably skip some details about how it is that networks optimize.
It's okay, maybe you go through and we arrange another lecture for other lecture. Just go by your love.
Okay, well, I will attempt to. Okay, so back in the day, it was noted that networks that have certain properties do, as activation flows around in a recurrent manner, steadily change a function to either increase it or decrease it, depending on which sign convention you pick. So Hopfield's convention was one in which the value of this function went down over time. Mine goes up, but the idea is that if we just write down this expression as a measure of the state A of a network with these weights of interconnections, and where the function sigma here is actually related to the input-output mapping that each neuron performs. Typically, it would look like this. This iota here is the net input to a unit. It's the sum of the activations of all the other units weighted by the strength of their connection to the given unit alpha. That's what this says. So the net input iota is filtered through a function sigma to produce a final output. And so if we, first of all, stipulate that the network must have symmetric connections. So the strength of the connection to alpha from gamma is the same as the connection to gamma from alpha. We take the derivative of this expression here, boom, 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 we get this. It's the product of the rate of change of A with an expression that depends on the difference between the net input and the inverse of the function that's mapping the input to output of a neuron. And this will always be positive if these two things both have the same sign. So either positive, positive, or negative, negative will always increase. And that will be the case in all networks that have the property that when the sign of this is positive, then this is positive. So the activation will increase whenever the sign of this is positive. We'll get two positive numbers. Or it'll decrease whenever this is negative. And this thing, the sign of this thing, since sigma is assumed to be a monotonically increasing function, we can just compute the sign of this by taking sigma of it, and it goes through 0 here. And we get this expression here. What this says is that whenever the activation of a unit is lower than sigma of its input, then the activation should increase. So this is an equilibrium value. Whenever the activation reaches it, the activation of that unit will no longer change. So it's a very general property of networks. If the net input to a unit is lower than some equilibrium value associated with its with that input, then it should raise its activation level. Otherwise, it should lower it. All the networks that work like that will. This
is the same proof.
I honestly don't remember the proof in the 82 paper, I have to admit. But this is for continuous units, not binary units. So it would be his 84 paper. All right, so now if we use equations like I just described to circulate activation in a deterministic fashion, then what we end up with are local maxima of the harmony function. So the state will increase its harmony to the locally highest peak, but that's not necessarily the globally highest peak. We can get global optima or global maxima of harmony by using stochastic networks that use randomness in their activation passing. So here's a stochastic differential equation that we use. The equilibrium achieved by this equation here is a Boltzmann distribution or a Maxent distribution or log linear distribution, or call it whatever you like. It's the exponential of the harmony of a state determines how likely that state is. So higher harmony states are more likely. And there's a randomness parameter, because this is a stochastic system, T, the temperature, that scales the effect on probability that different harmony values have. So if we drop the temperature to 0, as time goes on during the computation, as t goes towards the final time, we drop this computational randomness parameter temperature to 0, then the probability, according to this, in the equilibrium distribution will go to 0 for all of the states A except those that have the absolute highest harmony. The globally highest harmony states are the only ones that will have non-zero probability in that limit. So this is simulated annealing. It's been known since the 80s as a way of trying to find global optima. And in simulations, when you're using a discrete time update, delta t, then this is the formula that you use. You just add a random deviate here, which is Gaussianly distributed. So let's see here, right. And the dynamics that I just described is what I refer to as the optimization dynamics, because there's another dynamics that's important too. This is the optimization dynamics. All right, and what I mentioned is that there's a relation between micro desiderata and macro desiderata, or micro harmony and macro harmony, and that's given here. So if we have a tensor product representation as the state in our neural network, A is the image of this under this isomorphism of some structure S. It's the sum over all of the bindings in S of fillers to roles of the vector encoding the filler times the vector encoding the role, outer product. So it's the sum of vectors B, each of which has this tensor product form. So attending to this simple form, it's the sum of vectors, one for each constituent. We can ask what the harmony is of any state that has that form. And the answer is the harmony will be expressible in this way. It's the sum of terms for every pair of constituents in the structure. So if we think of this as a tree, then for every pair of elements in the tree, there's a term which could be positive if the grammar likes that combination, or it could be negative if the grammar says that such a combination is ill-formed, plus a term that just depends on the well-formedness of each individual constituent alone. So this is a form of a harmonic grammar. When we have a tree, we can state for pairs of constituents whether the grammar likes or dislikes them and by how much, by just writing down what the harmony is that it assigns to those pairs and to the individual elements. And given those rules, we can compute what harmony a given state has, whether we choose to calculate it at the level of the individual units in the micro level, or whether we choose to just analyze it in terms of the symbolic constituent structure as it is done here. You get the same number.
Equal, you need to have TPR. Otherwise,
yes.
You don't get that.
Right.
Okay,
that's right.
Okay.
That's exactly right. Okay, and so derivation is straightforward. I'll skip it here for that's true. Here's a little example of what one of these terms might look like in a syntactic context where, so this might represent any subject marked plural, and this might represent any verb marked singular, and this term in the sum, that is the well-formedness of a sentence, would have a penalty assessed by a constraint that we call subject-verb agreement. So dogs runs violates the constraint, incurs a harmony penalty. This is the magnitude of the penalty. So if that's a constraint that's strong in the language, then that'll be a large negative number. Okay, and it's just like we've already seen such things, but this is more explicitly about the relation between two things than is the subject constraint and the full interpretation constraint that we saw before. Okay, so that was kind of an aside about the underlying math to the assertions about the relation between the micro and the macro picture here. I already mentioned optimality theory a moment ago because I inadvertently slipped into thinking in those terms. So optimality theory is a variant of harmonic grammar. So everything we've said so far applies except that, first of all, there's a very strong commitment in optimality theory that the constraints are universal. They're literally the same in every language. So even though we use meaningless words like it in it rains and Italian doesn't, it doesn't mean that we have a constraint against meaningless terms and Italian doesn't. The constraints are the same in all languages. But rather than having different weights as they do in harmonic grammar, in optimality theory they have different rankings. So all the constraints in a language's grammar are ranked from top to bottom, and each constraint has absolute priority over all of the weaker constraints below it. And that's something you can simulate with numbers by just making the numbers, the strength of the constraints increase rapidly, essentially exponentially, as you go up the hierarchy to stronger and stronger constraints. And then if two expressions differ in terms of whether they violate a given constraint, the penalty will be so much higher than all the penalties of the weaker constraints that it doesn't matter what the weaker constraints have to say. Whichever violates the stronger constraint is automatically going to have the lower harmony value. So what we saw in English was that what's critical is that the subject constraint must outrank the full interpretation constraint. We used 3 and 2, but the numbers really don't matter. What matters is that the relationship between them, and so there's software to take a set of constraints and look at all possible rankings of them in hierarchies. There's a program that will allow you to look at all possible rankings of a given set of constraints, and each one of those corresponds to a possible language. And so you can see for a given set of constraints that you might be entertaining for your theory, what range of languages are predicted possible by it. Yes?
These numbers are changed. Like, for example, full interpretation. If you put the penalty to be 10 rather than 2, I mean, the order will change.
The order is the only thing that matters. The magnitude of the number doesn't matter as to which one is preferred. Now, in a harmonic grammar, the probability of a structure is exponentially related to its harmony. So if you take the dispreferred form, which has lower harmony, and you make its harmony really low, then that will make it a lot less probable in the probabilistic version of harmonic grammar. There really isn't a probabilistic version in the same sense of optimality theory. The numbers are needed to make a connection to probability. Okay, all right, so there's some, all that's left in this little part of the talk is advertisement for optimality theory, which I can skip. Or just relegate to the handouts, okay. Yeah, and I had an example from phonology of a much more realistic set of constraints and how constraint interaction works in optimality theory. But we can talk about that another time or not, at your pleasure. Part 4 next week? Okay. Okay, I can't do Friday next week, but I could do earlier in the week because I'll be at Stanford on Friday. And in transit on Thursday, so sometime earlier next week I'd be happy to do.
Not Monday. We'll give you time to organize part 4.
Okay.
Tuesday or Wednesday.
Tuesday or Wednesday.
The half of this talk that's ungiven is already prepared, so I could do it on Monday too.
You talk about that at Stanford or Friday or different topic?
What I will talk about at Stanford is the stuff associated with the 4th of the general points that I started with, the one that was down here, about gradients in representations. I can try to do that, but then we might have to have a talk on Monday and Wednesday.
Okay.
Well, it's thank you very much.
Okay.
We're your stand now.